I just want to make a comment following David's story. Announcement. Sorry, what David said about the Fields medal. So, news the Fields medalist, Culture Beer Car, actually worked out some of his work, his paper at NCTS. So we are honored to be mentioned in this paper. So since you're all here, I've got a great chance to the next Fields. Okay, so second talk is by our TA, lovely TA, Gwen Lin from Penn State University,
Greater Allegheny.
So you'll talk about multi-reason algebras and Tory systems.
Okay. So first of all, thank you, Dave and Hao, for me can come home to eat good food and all the junk. And then second of all, thank you, Kato. You have been working very hard. I know I'm very pushy, but the group work is already decided before we started. I'm not the one decided, so blame those two. And then finally, if you like to write notes, just take a copy for your note writing. And if you have a tablet, please just download it from website, write it. You know what I'm talking? I have enough copy, should be okay. And then so sit tight, enjoy it, and then here is some firework. As I say, maybe someday you're going to become field medalist, and then so hopefully this is going to happen, right? So I'm going to talk about multi-reason algebra and Tory dynamical system. This is a joint work with Dave and Gabriel Sosa. So afterward, if you have a question, ask Dave. And then and outside, I wrote about the chemistry. So this is something related to chemistry. So I haven't taught chemistry since high school. So you have questions regarding chemistry, please don't ask me. But you can ask me about research, but I'm totally fine with it, okay? And so first of all, the first part of actually maybe 1/3 of my talk would only primarily introduce you the idea of chemical reaction network and Tory dynamical system. And once you have a solid idea, then I give you the connection, research algebra, multi-reason algebra. Actually, tell you what is multi-reason algebra first, and then finally the connection. Okay. Hopefully you enjoy it. Even you don't enjoy it, please pretend. So a lot of example I have on this talk is primarily from actually last year. There's NSF CBMS Regional Research Conference. Dave is actually the primary lecturer. He gave 2 lectures each morning, and then Hao is also one afternoon lecture. And then it was slide talk, boom, boom, boom. And then so that's what. And so most of the examples coming from his talks. And so if I make any mistake, and they correct me, refer to his lecture slide. Okay? So here is the first chemistry equations, and then it say if you have chemical reaction like 2NO plus O2, and then constant rate potential corrosion for the K, and produce 2NO2, right? And then I know it's very weird. American kids probably call it a nitro oxide and oxygen and those names. Those names don't talk to me. And so I'm going to just use the short terms, okay? And so this is the very first chemical reactions. And I'm going to introduce you the chemical reactions actually is related to differential equation. Now you're all awake, right? Very good. So how do you relate the chemical reaction? It's differential equation. It's very simple. It's very cute. So NO is one of a species. And the rate of the change of the NO with respect to the time t is equal to negative 2K NO2 squared O2, right? I have to explain why negative 2. Negative 2 is because you have, here you originally have 2 NO, right? After the reactions, you have zeros NO. Right? So 2 of it becomes 0. So it's negative 2K. Is that clear? And it's depending on how much ingredient, the species you put in at the beginning of the reaction network, right? So it is depend on the NO. This 2 is also square. That makes sense? And then there's a plus, so it's multiplication for the O2 here. Okay? Now let's do it again for the what? Oxygen, right? So for the oxygen, the rate of a change of the oxygen with respect to time t, originally there are 1 oxygen. After reaction, it becomes 0 oxygen. So it's negative K, but it's still depending on, at the beginning, your quantity of NO and O2, right? But here you need square, it's because there's 2 here. Does that make sense? Yes? And then we can do the NO2. Now NO2 originally from the right-hand side of your chemical reaction is 0. After the reaction, it becomes 1. So it's become 2. So it becomes 2K. Am I right? Yes? And then I still depend on this. Right? Now, writing chemical is really confusing me, so I'm algebraist. So primarily, we translate. How do we translate? We translate NO become S1, O2 become S2, NO2 become S3. Okay? And now the 2NO plus O2, it becomes S1 squared S2. 2NO2 become S3 squared. And now I have very clean differential equations. Does it make sense? Yes? Okay? Now we have enough fun, right? So I'm supposed to do example. Are you ready? And I have Barbary for this. This is copycat from him. He always like bring stuff. So if I have this chemical reaction network, right? And I have this is K1, 2. This is K2, 1. This is K2, 3. This is K3, 1. Can you see it? Is it too small? It's okay. Okay? And then if I call this is the very first one complex, and this is my second complex, this is my third complex. Yes? And then if I ask for A is equal to S1, B is equal to S2, C is S3, D is S4. Now my very first complex, A plus B, is supposed equal to what? Thank you. Who answer it first? Ready? Let's do it. Catch it. To see. It's baseball and here is very bad. And then can you? Who answer it? This is. He doesn't want to take it. It's okay. You're gonna take it to see if. Oh, I'm sorry. I try to get a heavy one. They don't have heavy one. The rice quicker. Usually I have chocolate. It's quicker. Anyway, this should be easy. Am I right? So I actually have totally 3 complex, and I actually have 4 species. Species are A, B, C, D. Right now I all translate like S1, S2, S3. Sounds good? Now, because here you can think about is monomial, right? And so you can track it. You can have exponent vector 1, 1, 0, 0. And then you have another exponent vector 0, 0, 1, 0. And you have third exponent vector 0. Sounds good? Now let's see if you really understand how differential equation work. ds1 dt is equal to, anyone volunteer? No? Let me do first one, and then how about you do the next one, okay? So ds1 dt, where's s1? S1 is A, right? So we have to look everything related to the A. who are related to the A is negative K12 S1 S2. Am I right? And then positive K21 S3. Yes? And then positive K31 what? S4. Are we clear? Yes. And this is negative K12. I'm going to be lazy. This is Y1, 2, 1. Y2. Y, Clear? And this is actually also equal to what? ds2 dt. Agreeing? Yes. And how about ds3 dt? Who want to answer it? You have to raise your hand and answer it. Otherwise, you always get to answer the question but not eating it. Who want to answer it? Come on, kiddo. 1. K. Crap. I did something. No, this is, oh, I know. Is it right? Yes. So, now you, it's okay. Actually, you know what? I'm going to skip it to this program. Because there is a keynote, it's still unstable. So, it's this one. It's okay. You're intelligent. That keynote things is very new, and just you know, the Apple is just playing with it, and it's getting better. And you can insert log text, and such that you can print out nice and neatly. And then mathematicians no longer give up boring talk anymore. Yeah, but it's still unstable, so I'm using you as guinea pig. Now, Ben, come back to you. K, S1, S2. That's it? That's it? Minus K, 2, 3, 3. Am I right? Every reaction, the error, you have to consider. Are we good? Yes? I'm going to take this, and then you're going to answer it correctly next time. And you can earn it. Right? This is okay now. I'm going to go in. Otherwise, nobody get to party. Am I clear? So you had differential equations. Now, this whole writing is really tiny, right? So one of the things I told my student, mathematician is the most lazy species in the world. We invent the notation such that we condense word. And the whole differential equations, if you put the ds2 dt in the middle, you can rewrite it as product of matrix actually. Now you all did linear algebra before, so I trust you have this ability to rewrite. Sounds good? Yeah, you totally believe it, right? So as long as you do it correctly. And by the way, this finished writing versions will be posted on the web as well. So the one you just have it now is a hybrid, is blanket, so the kids want to write, they can write it, right? But my handwriting right now, when I'm giving the talk, is miserable. So you can see the nicer handwriting. I will post it. Sounds good? Okay. So this is the differential equation we care, and we still want to write it even shorter. We're going to write this is Y matrix, the exponent matrix, and this is AK matrix. Okay. And then this is the phi S matrix. Am I clear? So I'm just teaching you translation now, right? Not much mathematics. And so here is the official definitions of chemical reaction network. You have an N species. Those N is the ABCD or NO2, O2, that kind of stuff. Those are species. And then we translate into S1, S2, S3. Okay? M complex is what? A plus B is S1 times S2. It's the complex. Okay? And G is the weighted direct graph. Why weighted direct graph? This is a graph, right? Yeah, and directed. Why weighted? Because we suppose put on the reaction rate, right? Yes. So we call it weighted directed graph. Is that clear? Yeah. And so the weight on the edge would be I to the j would be reaction rate. We write small kij. Sounds good? Okay, so this is a whole package of translations. And steady state or equilibrium solution is a solution such that the rate of the change of each species is actually equal to 0. And so you're supposed to take differential equation, you're supposed to know this. Right, it's called equilibrium solution. Sounds good? Yes? Let's look at more example. So this is the same chemical reaction, right? Yes. And then we want ds dt equal to 0. What does this mean? Is this everything equal to 0? In order to everything equal to 0, we have to have this equal to 0, which is mean either this one or this one have to equal to 0. So this is actually boring cases. If we want an equilibrium solution, we will run our reactants. Am I right? And so here is more interesting example. We want to, people are interested and we want to work it out. Is 2NO, this one, N2O2. And so this is K12, K21. And this, if I call it S2, this is S1. And so my exponent vector, Y1, will be what? 2, 1. Remember this 2, right? This exponent vector. Y2 will be 0, 1. Sounds good? And then differential equation, ds1 dt will be negative 2 K12 S1 squared plus I'm doing S1, right? And after K12, I lose it. So it's negative 2 K12. Is that clear? Yes? And then positive 2 K21 S2. Cool? And then ds2 dt will be what? K12 S1 squared minus K21 S2. Am I right? So in order to get ds dt equal to 0, what do we do? Is K12 S1 squared equal to K21 S2. Am I right? This is more interesting, right? So as long as those K reaction rate and also the amount, the quantity of species you put it in, satisfy this equation, you're going to reach equilibrium solutions. Sounds good? This is what the biologists and the chemists, they care. They want to figure out when this happens. This is always this case. Clear? Now, so before I really give you, half of people stuff on this. So I give you a chemical reaction, and we want to figure out when it is reach stable equilibrium solutions. And a lot of time, life is rough. You're not going to get perfect. The purpose 2 cases. So what do you do if you have conjecture and you couldn't prove it? What mathematician do? We can put the assumption in, right? Here's the assumption. Okay, so assumption is if you have a connected component, what is the connected component? You just have a whole chunk. Everyone is connected. So you have a connected component, weighted direct graph, and we call it is strongly connected. It means what? You have a reaction from here to here to here to next one. from here to here, then you always can come back. Okay? This is, you will give me twinkle eyes. So C1, go to C2, go to C3, right? Yes? And then C3 can always go to C1. Then this is, we call it strongly connected. Sounds good? As long as you have one go to the other, then you always can able to come back. This is called strongly connected. Actually, am I right? Is this strongly connected? I need this one in order to make it strongly connected. Yes. Because why? If I go 1 to 2, do I have anything from 2 to 1? I don't. So this is not good enough. Am I right? Yes, I do. Because, yeah, I have 1 to 2. I always can find a way to come back, right? So I just do 2 to 3, 3 to 1. Yes? So this is strongly connected. If I go from 2 to 3, can I from 3 go back to 1? Yes. I do this, right? If I go 3 to 2, do I have a way to come back? 3 to 2, can I go from?
Just narrow from 2 to 3. You can just go from 2 to 3.
Oh yeah, stupid me. I just said that, right? I think this is Johnny Connect. I remember, right? This is Johnny Connect, right? So when it's not strongly connected, or weakly resolvable network, C1, C2, C3. This is the one I say. This is not weakly resolvable, right? Because of this.
Because if you go from C2 to C3, how do you get back? The wall set.
This is not.
Ah, okay.
You have a 2 to 3. 2 to 3. Can you go 3 to 1 is okay. Which direction goes wrong? If every time you have a connection for any two, right, I to the J, you also can find a way to come back. I have this one, so I must make a mistake. Very good. How do I change it? Very good. You are awake. Right now this is not weakly resolvable. Okay. So another definition. I have hard time to pronounce this. I try many times. It just wouldn't work for me. So key matrix subspace. So it's a chemical reaction network such that you take the span of the as long as you have age from I to the J. And you take the exponent vector into the subtractions, and then you take the subspace, okay? And then this is big. Fenneberg, he proved that he proved something big, and I need to give out definition deficiency. Deficiency of a chemical reaction network is delta. Delta is M minus L minus S. M is number of complex, everyone can count. L is a kinetic component, everyone can count. This is the dimension of the stoichiometric subspace, okay? And so this is what it defines and why we people care. I have to give example before I tell you why people care. So let's do example so that you really understand what does it mean. Sounds good? Examples. A, I don't want to do the green. Are you following me? Yes, thank you. A plus C, this is D, this is B plus A, okay? And I give you the name 1, 2, 3, 3 complex, yes? And then I have matrix, exponent matrix. Can you read off exponent matrix? A, B, C, D, E is corresponding as 1, as 2, as 3, as 4, as 5. Can anyone give me the exponent matrix? Yes? Good job. Yes? Are we clear? Yes. And then what do you do to get the space? We have m equal to 3, l equal to 1, right? What is s? It's the span of y2 minus y1. Am I right? And then y1 minus y2. And y3 minus y1. And y2 minus y3. And actually, this is the same as the span of y3 minus y1, y2 minus y3. Yes? And then the dimension s is 2. Am I clear? And so, what's my differential? 3 minus 1 minus 2 minus 0. All good? Listen. So, deficiency 073 is home. He proved that it's he or she, I have no idea. A chemical reaction network is complex balance for every set of possible positive reaction rate K, if and only if it has deficiency 0 and is weakly resolvable. This is very significant, which is mean if you have a chemical factory and you can totally hire a dummy, as long as your chemical reaction satisfy those conditions, and the dummy can just make the temperature maybe 100, 200, it doesn't matter, going to reach balance. Because the K is the reaction rate, right? If you know a little bit chemistry, K is depending on the heat you're putting in, stuff your human make a factor of it. And then all you put a species in. So no matter what, you would have, you would reach the balance. Does that make sense? Yes? And then this is a big shot. They prove something. It's a new definition they define. After this is very big, strong theorem actually, because in general, the deficiency is not 0. In general, this is not true. So once someone proves something very strong with a strong condition, what do you do next? Weaker the assumption, right? And so those 4 people, they define so-called Tory dynamical system. Right, and what is this? You have a differential equation of this form. And not only that, it has positive. Chemistry, biology, people only want positive, complex, balanced state solution. Which is mean your S's have to be positive. Because, you know, differential equation could have negative solution. We only care about positive solution. They define this, okay? And more example, okay? Any questions so far? A lot of chemistry, I know, but you're gonna share at the end. I promise. Okay, be open-minded. Now, I'm gonna give you another example. It's A plus B. Yes. And then I have 1, 2, 3. Yes. And then some of you have a little bit of a complementary, some don't. If you look at the complex ones, can you draw a spanning tree such that the 1 is the final sink? Spanning tree. For example, this is a spanning tree. Am I right? And 1 is the final sink. Yes? And what do you do? This is K3, 1. This is K2, 1. Yes? Okay. Now another spanning tree for the 1s. What do I do? 1 is the final sink. For example, like this. Yes? And so what is this? K2, 1, K3, 2. Am I right? Let's get another spanning tree. Maybe this way? Yes? And so this is what? K3, 1, K2, 3. So I'm going to define capital K1, the big one, is the 1 here, okay? is actually K31, K21 plus K21, K32 plus K31, K23. Okay, this is my capital K1. And you can do this for the second complex, right? So what is the second complex? Like this, right? And so you can do the K2 is what? K12, K32. Am I right? And then you can continue 31, K12, and K13, K32. And then the next one, the third complex, okay? K13, K23 plus K21, K13 plus K12, K23. Yes? And then why we care? Because this is so-called matrix tree theorems. It says the kernel of the AK, remember the AK? The matrix, you put all the 22 called K, right, in, is spanned by what? K1, K2, and K3. Okay? Why this is true? Because this is weakly resolvable. As long as you have strongly connect or weakly resolvable, you can apply matrix tree theorem and to construct all the spanning tree. And then for each complex, you define those K. Sounds good? And then you got a kernel of your matrix AK. Why care about AK? We're finding ds dt equal to yak vs equal to 0. Am I right? This is why we care about AK, kernel of AK. Right. So in order to get this equal to 0, we need what? S1 squared is the Vs, right? S1, S2, and then S2 squared. Remember? This is corresponding to S1 squared, S1, S2, and S2 squared, right? These have to be multiple of the kernel spanning, right? Yes? And then if you want to kill the lambda, because you just need any multiple, right? So you need to find the relationships of the radiation rate such that to make magic carpet solution, equilibrium solution. Am I right? So if you know your calculus 3, you're supposed to Lagrange multiply along some elimination. You're going to see this is the relation. You have to satisfy. Okay? Does this look familiar? It doesn't look familiar? How about this? Does this look familiar? This is what? What? This is a Toric. Yes. So actually, those 4 big shots, they define Tory idea, co-TG. Okay? How do they define it? Is you do the K1 S1 S2 minus K2 S1 squared and K1 S2 squared minus K3 S1 squared, K2 S2 squared minus K3 S1 S3. And then you current with, did I make a mistake? Which one is S?
K3, S1, S2.
K, this one, S1, S2. Let me see. A plus A plus B. This is B plus B, right? And then,
Oh, okay. Wrong.
thank you. You're away, very good. Sounds good? You have to do the Cohen saturate. I read it K3, S1, S2. Let me see. This is 2, 3, right? And then suppose S1, S2. Very good. Suppose S1, S2. I don't have S3. Do I have S3?
No.
I don't. This is really silly on me. No, I do have K3, but I don't have S3. That's right. You take saturation of it. This is, you call it Tory idea. Okay? And then another idea is called complex balance idea, or complex balancing idea. Will be which one? MG is just TG intersect the QK. Okay? Why? Because this TG, if you do the computations, actually I forgot the computation. I didn't write it down. Anyway, will be exactly this one. Okay. Yeah, so that's why they call it Toric. It makes sense. Not only that, the delta is actually the dimensions of the Q, K, mod, MG. Okay? And I'm going to give you their picture. If you have a kinetic component of weakly resolvable chemical reaction network, then your TG is actually a Tory idea. And then you can get your NG by intersecting the QK. Does this make sense? Okay. Enough chemistry, right? Let's move on to algebra. Okay. Sounds good? Yeah. I don't have much time, so you can see it's not hard. So, multi-risk algebra. What's multi-risk algebra? Probably some of you haven't heard about it. Let's start with basic so-called risk algebra. And some group you did homework, and homework had risk algebra, right? Yes. And it's exactly what it is. Okay. So suppose you have a field K, and you consider it's a polynomial ring. Only consider K join S, and then S are the variable S1 to SS. The risk algebra of n idea I in a communicated ring R is a graded R algebra, and what it is just the sum of I to the n. Okay, and then for or you can say R join IT, and this is not what we really interested in terms of presentation. What does risk algebra? How do you write it out? What we really care is suppose you use the R join new variable. This is my cheat sheet wrong. New variable K1 through K out, and you send the map and R join IT by defining KI to the FIT. Okay? Then the risk algebra of I is actually isomorphic to the R join the K variable mod out the kernel phi. Okay. What we care is the kernel phi is the defining idea of the risk algebra. Does this make sense? Okay. So when I first learned risk algebra at the beginning, when I was young, it's really scary because what does it mean? The result of infinite power, right? Later, I really like this because what I want is just write my risk algebra as quotient of polynomial ring. And this is much clearer, right? So this is the idea. And the multi-risk algebra is similar idea of presentation, but the notation-wise, it will be more intense. So you have y1 through yn. Those are exponent vector. You make a partitions on 1 to the n. And each idea ik depends on the partition you have. And then you define a module such that this is the result of your idea. And then you take its Riesz algebra by looking at this ugly. Okay? Again, this is something I don't like. Nobody like it. So this is what we like. Is instead of looking at the infinite direct sum, we look at K1 through Kn as a variable. We join in as I did it before. And I define a map from the Rk to the Rt, right? What the T? T is T1 to T2, T, small t. We have been lazy. And then I send my Ki to each Syitk, right? Depending on my Ki is in each partition, right? And so what I want is finding defining ideal of multi-Riesz algebra. Does it make sense? Okay. And I'm going to give you one example. Actually, I'm just throw you a theorem. It's faster this way. TA is what? The one, just like previous one, I start with the chemical reaction. I take the exchange reactions. For if you're more algebraic, it's called 四式 reaction. You take all the 四式 relations and you colon and you with the product of all the variable, you collide and saturate it. And then we call it TA. Does it make sense? But right now, because we have each partitions, right? So the 四式 relation, I only take each partition 四式 each partition 四式 I don't take 四式 of first partition and second partition. That's why the condition AK come in, because you only take the 四式 relation inside the same partition. Does that make sense? And then this TA is actually a Tory idea. You don't see it, but you can prove it. Sounds good? And you want an example? Yeah? Everyone like example? Right. So here is SY1 equal to S1, right? SY2 is equal to S1 squared. SY3 is S1, S2. And SY4 is equal to S3. And SY5 is equal to S5. All good? So I actually have 1, 2, 3, 4, 5 generator. And I take partition using 1 and 2. 3, 4, 5. All good? So A1 union A2. Yes? My idea I1 is corresponding to S1, S1 squared. My I2 is S1, S2, S3, S2. Something is bothering me. Must be typo. It's supposed to be S2 or S5. I think this is wrong. Should be 2. Sounds good. Then my idea, my M, I'm looking for is I1, I2. And then we are looking for this Riesz algebra of M. Okay? Yes? And then we want to, this is actually R join K variable mod out the TA. This is actually in the next theorem. But the TA is actually, I just take K, I didn't write it all out. Ki yj minus kj syi. And then but ij have to be in the same partition. K1, 2. Is that clear? Yeah. And we do product of Si and I saturate. And for this one, I write out the generator for you. K1, K3 minus K2, K5. K1, K3 minus K2, K5. Yeah. And then K4, S2 minus K5, S3. And then K1, S1 minus K2. And also K5, S1 minus K3. This is how you saturate and then you see it. Okay. Do you know saturation? You know, right? Yes. So this is TA. And then the risk algebra we find is actually the TA here. Sounds good? Connection and result. Everyone is like, what the heck? Two different things, right? If you're sharp, you already see it. This stuff is extremely similar or actually kind of identical to the one strong field the 4 people define, right? So the connection is, suppose G is the direct graph coming from the chemical reaction network. That is also weakly resolvable. Suppose G is connected component with G1 through GL. What do? You set TG in this way, which is, again, for each connected component, you take the Suzuki relationships and Cohen and then take the saturations. You define TG this way. This is what we prove is the TG is actually just TA. Okay? And then, of course, it's a Tory idea. So what's a bit different of what they did and what we did? They only did one component. We did multiple components. Not only that, we made a connection of race algebra and the chemical reaction network. This is our big contributions. And then, do you want an example? Actually, I can come back to this example, right? Can you recover the G for me? What's the G? If I make S1 is the A, right? So I can do what? A to A is the first one. Yes? And the second one, what do? I do A plus B, yes? And go to C, and then go to B. Are we good? Yeah. So if you have 2 chemical reaction network, and then you can just associate with monomial ideas, and then 2 component, then it's direct sum of 2 monomial idea. And then if you know risk algebra, then you know the chemical reaction network, the complex balance idea solutions. And not only that, because this is discovered, you can notice everything is purely algebraic. As long as you have weakly resolvable, then you can use matrix tree theorem. And so no matter what kind of the direct graph you already have, you add more graph, they make no difference. Actually, I gave a talk, and there was a chemistry in the audience. They say a lot of time for the chemistry people, they assume it's always 2 sides anyway. So the condition on weakly resolvable is actually harmless. Does that make sense? Yes. And this is something more algebra. The spatial fiber is something you tensor with the K. And because we talk about blow up, I haven't done the translation, I forgot, because it's not on my cheat sheet. So what is risk algebra? Is the blow up of the spec up along the idea, right? And here, spatial, so risk algebra is corresponding the graph. And then spatial fiber is corresponding to, because you do tensor, will be the image of the graph. Okay, and then as long as each component, they are the same size, then the spatial fiber, defining equation of spatial fiber, is actually the chemical reaction, the balance solutions. Okay. And then I'm going to change my mind because David talked using the one example. How good is this result? And so far at this point, suppose this is your chemical reaction network. Okay. And then remember, each complex, I make it K1. Yes? And I have K2, I have K3, I have K4. I can just read off this graph, tell you the MG, the modular idea. just K1, K3 minus K2, K4. And this is actually what they have as Y minus GW star. And it's exactly the same star, as it's just different, the name, different name. You know what I'm talking? And why? Because AB is corresponding to whom? S1, S2, right? And BC, S2, S3. CD, S3, S4. And this F4, F1. This is how I see it, okay? And then so I should do the thank you things and the citations. I have 2 minutes. I want to share the story of why we start this project. So the conference started last year, and then before that, I knew Dave is the main speaker, and I knew he's this fantastic speaker. And so I just applied to go, and hopefully they pity me and give me money. So now they pity me, they pay the dome, they pay it full. I just need to pay the air ticket. And then luckily from Pittsburgh to Dallas is $200. So I totally can afford it. So I just went. And the thing is, I know David is great, but if I don't prepare, I learn nothing. So he is great. He prepared all the slides, everything ready, and even have lecture guide. So I download everything, download all the paper I could find, and put it in my folder, and then start reading like a week before and everything. And then I have the idea of this workshop going to be intense, and it was 5 days, 5 mornings, each morning 1 hour, and then so many slides. And as long as I can learn 3 days, I'm happy. And then so it was related to research bar, geometry modeling, elimination, rigidity, and chemical things. Which one is not on my list, say I must achieve? Chemical. Because I've been taking chemistry since I was high school. So when I went in, but I'm still a good student, I still read. And then, of course, many parts was very shaky, and chemistry was the final day. And I still listen. And I asked him questions after the talk, and then tell him like, this is just research, bro. He didn't believe me, of course. So I sent him an email on Sunday. I touched him on Saturday, sent him email on Sunday, and then crazy. I dropped everything, including kids and husband, just work with him because he like best for email. Crazy. 2 weeks after, paper on archive. Right now, it's published. You could be one of me at the time happens. Yeah, so be open mind. It's always trying to think, and then it will come. Okay. That's right.
Ask
Yeah.
a good question.
Yeah. So yeah, ask question. Don't be afraid, because I never ask question in front of the whole audience, but I do hands-on speaker ask some question publicly sometimes. If you are like me, don't like ask question publicly, it's okay. But talk to people is okay. And then right now, even I go out and give the talk, I will have people come to talk to me, and later we start cooperating. So I'm in the campus. I'm the only mathematician. But last year I have 4 papers, so you can do it.